In 1990, Northrop Grumman rolled out a new black airplane, a sleek, angular fighter with diamond-shaped wings and a cockpit pushed far forward on the fuselage. It was the YF-23, a contender in the Advanced Tactical Fighter competition to build the U.S. military's next great fighter. This fighter would need to be stealthy, supercruise, have high maneuverability, and carry a variety of air-to-air and air-to-surface weapons. But the YF-23 did more than meet those requirements. It rocked the aerospace world. The YF-23's sharp angles and lack of radar return were like nothing anyone had seen before. And that got everyone wondering, how can we use this to make an even better fighter? While the YF-23 didn't win the contract, its innovative design introduced concepts and technologies that later found their way onto the Joint Strike Fighter, the F-22 Raptor, the F/A-18 Super Hornet, and the F-35 Lightning. In some ways, the YF-23 may have been more influential as a technological pathfinder than if it had itself become a frontline fighter. We know today that there are two main methods for reducing an aircraft's radar cross-section, or RCS. One is to use radar-absorbent materials, composites or coatings, to absorb radar energy. These are very effective, but add weight and degrade over time. The second method is to use clever shaping to redirect radar beams away from the observer. This is trickier, but has the advantage of not degrading over time. And while both methods are still used today, the YF-23's design focused entirely on the second approach. Using computational fluid dynamics or CFD and wind tunnel testing, designers mapped radar waves around the aircraft, bouncing them off the edges and control surfaces and deflections of the aircraft to find any and all methods to avoid presenting a big radar return. Because of its unusual angles and small details like the serrated third wing panel, the YF-23 managed to reduce its RCS to that of a small bird flying straight towards a radar array. Now, when we talk about stealth fighters, especially those built after 2000, most people assume they have the same look, a faceted, highly reflective appearance. This stems from the F-22 and F-35 designs, which use facets to specifically reflect radar waves back towards the source. In aviation terminology, this is called being edge-launched. As you might imagine, this makes it much easier to detect an aircraft on radar because the radar beam is literally bounced back by these facets. In fact, if you take a look at the F-22 Raptor, you'll see that the designer added several facets to the sides of the jet intakes to help with this. But the YF-23 did something completely different. Instead of reflecting radar waves back to the source, it diffused them. The YF-23 resembled a small boat moving through the water with its bow facing directly towards the radar source. This approach works well because the radar waves are scattered in all directions, resulting in a weak signal. Unfortunately, this approach doesn't work well for supersonic aircraft because the intense heat generated by air friction at those speeds requires a heat shield. But the YF-23 managed to pull it off, thanks to its powerful engines and advanced materials. The YF-23 was powered by two Pratt & Whitney F119 turbofans, the same ones used in the YF-22, but the YF-23's designers were able to coax more power out of theirs by trading off thrust for efficiency. Unlike the competing YF-22, the YF-23 ditched afterburners entirely. This allowed it to achieve sustained supersonic speeds of Mach 1.4 without the speed-robbing inefficiency of burning extra fuel. It was the first fighter ever to do so. This was made possible by the YF-23's highly efficient diamond-shaped wings, which reduced induced drag below the thick, less efficient wings of the YF-22. This meant the YF-23 could achieve a range of 600 miles at Mach 1.4, or 1,600 miles at subsonic speeds, compared to the 700-mile range of the YF-22 at subsonic speeds. Today's Supercruise remains a holy grail of sorts in fighter design, something engineers dream of but rarely achieve. Aircraft designers have attempted to use boundary layer ingestion and other techniques to allow future fighters to enter supersonic speeds without using afterburners. But how does one go about achieving a sustained supersonic speed? In short, it comes down to three factors: power, aerodynamics, and cooling. Let's start with power. With no afterburner, the fighter needs to produce enough thrust at high subsonic speeds to accelerate to supersonic speeds. So while the YF-22 had to drop down to lower subsonic speeds to conserve fuel, the YF-23 could maintain high subsonic speeds without wasting fuel. That's partly due to its efficient wings, but also thanks to its two powerful engines. Next is aerodynamics. At subsonic speeds, the YF-23's wings generate lift in a slightly curved bubble above the wing. The air flows smoothly over the top of the wings, creating low drag. At transonic speeds, however, the air flowing over the wings compresses and the pressure increases. To prevent the formation of shock waves, which increase drag significantly, the YF-23 used strakes near the leading edge of the wing to move the transition from subsonic to supersonic flow further along the wing. Additionally, the air flowing along the top of the fuselage separates and reattaches at what is called a shock diamond. By manipulating the angle of the fuselage, the YF-23 minimized the size of this shock diamond, minimizing associated drag. Finally, cooling. When air friction heats up the intake, the hot air expands, reducing the amount of air entering the engine and reducing thrust. To solve this, the YF-23 sucked in cool air from just outside of the heated intake, providing the engine with a steady supply of cold air. While all these measures were necessary to sustain supersonic flight, YF-23's real claim to fame was its unique radar-defeating airframe. Remember, the goal of stealth isn't to be invisible, but to avoid detection by enemy radars. And the best way to do that is to deflect the radar beams away from the source. Today, most aircraft use facets or flat planes to accomplish this. But when the YF-23 entered the race, no one had really explored this idea yet. Everyone assumed that low observability would come from aircraft like the SR-71 Blackbird, with long, smooth curves that deflected radar beams away from the aircraft and behind it. For example, the upper surface of the fuselage and the back of the cockpit were shaped like Pringles chips to deflect radar waves away from the aircraft. But the problem with this approach is that it's hard to hide the aircraft's vertical profile. Today's stealth fighters get around this by using the S-shaped ducts to route the radar beam over the aircraft and away from ground observers. However, these ducts add weight and complexity and are extremely expensive to build and maintain. So the YF-23 tried something different. Its most famous feature was its small radar cross-section, but it wasn't its only one. After all, an aircraft's radar cross-section changes depending on its orientation relative to the horizon. So the YF-23's designers didn't try to reduce its RCS from the front or the side. They worked on reducing its RCS from the rear. The idea was that if the YF-23 could present a small radar return from the rear, then it could simply fly backwards, turning its tail towards the enemy and deflecting radar beams away from its faceted nose. Some reports suggest that the YF-23 managed to reduce its RCS to 0.01 square meters or less from the rear. This meant that if the YF-23 flew with its nose pointed at the sun and its tail pointed at the enemy, it would be almost impossible for the enemy to detect it. While the YF-23's designers probably thought they had solved the problem of radar stealth, the Air Force didn't buy it. During the flight tests, the YF-23 was equipped with an onboard radar system. But when the pilots flipped the switch to turn it on, they noticed that there was already a blip on the scope. The radar system had detected the aircraft during takeoff. It turned out that the YF-23's designers had failed to account for a small but critical detail: the pitot tube. Pitot tubes are used to measure airspeed and are a standard piece of equipment on practically every aircraft. But the YF-23's sleek design left little room for a traditional pitot tube, so the designers installed a tiny one right under the fuselage. The trouble was, this pitot tube broke the smooth contours of the rear of the aircraft, breaking up radar waves and betraying the aircraft's position. After discovering this flaw, the designers revised the YF-23SS, adding several small fillets at the base of the wing and strakes to smooth out the airflow around the pitot tube. But by the time they made the change, the Air Force had already awarded Boeing the contract to build the next generation of American fighters. So why did the Air Force choose the YF-22 over the YF-23? The answer is simple. The YF-23 was too extreme. It was lighter and faster and harder to detect from the rear. But it lacked other qualities deemed essential by the Air Force, notably its ability to turn tight corners. When the two prototypes were put through a series of aerial maneuvers, the YF-23 turned out to be slower and less agile than the YF-22. Unfortunately for the YF-23, The Air Force wanted a fighter that could perform a wider variety of missions, including dogfights. So, they chose the YF-22. In the end, the YF-23 may have lost the fight, but it won the war. Not only did it introduce concepts and technologies that later appeared in the F-22 and other fighters, it also served as a warning of sorts, a reminder that stealth wasn't a one-size-fits-all solution to national defense. Today, the Pentagon keeps a close eye on emerging technologies and foreign fighter programs, making sure America stays ahead in the arms race. Thank you for watching.